Okay, so a bird sits on top of a lamppost. The angle of depression from the bird to the feet of an observer standing away from the lamppost is 36 degrees. The observer is 20 feet away from the base of the lamppost. How tall is the lamppost? Round to the nearest foot. So this is going to be one of those problems where it'd be really helpful to have a picture. So let's draw a picture. So we know we got this lamppost and the bird sitting on top. So let's stand our lamppost up. Okay, bird's up on the top. I'm not going to draw the bird. And it says we have an angle of depression from the bird to the feet of the observer standing away from the lamppost. So they tell us that that angle of depression is 36 degrees, and that observer is 20 feet away. So if our lamppost is here, okay, our observer is standing 20 feet away. Let's say that they're standing over here someplace, right? 20 feet away. Okay, we're trying to find the height of this lamppost. Okay, but they give us an angle of depression. Remember, the angles of depression are measured from a horizontal. Okay, and these horizontals are going to be like parallel to the ground here. So we know that these are parallel. So if they tell us an angle of depression, it's measured down from that horizontal, is 36 degrees. Now, if these two lines are parallel, this is a transversal. So that makes this 36 degrees as well, because these are alternate interior angles. So now this is a trig problem, because we've got an angle, we've got a side we know, a side that we don't on this right triangle here. So let's write down our functions here. SOHCAHTOA. Sine, cosine, and tangent. Okay, so what do we have? So everything's in relation to the angle. So if we've got this 36-degree angle here, it's all in relation to that angle. Well, the x is the opposite side away from that angle. The 20 is adjacent because we can see that it's touching here. So we have an opposite and adjacent, so we're going to be using our tangent function. So let's write down our tangent function here. So we've got the tangent of the angle that we know, the 36, is equal to our opposite over adjacent. So the x over the adjacent, 20. So since our unknown is in the numerator, we're going to multiply the side that we know by the function and angle that we know. So that height is going to be 20 tangent 36 degrees. 36 degrees. And they told us to round this to the nearest foot. So let's round this to the nearest foot. So 20 tangent and 36 degrees. Enter. So 14.5, that 0.5 is going to round that 14 up to a 15. So we're looking at approximately 15 feet for the top of our lamppost. Okay? Next problem. Now we've seen this problem before. Tom is constructing a fence around his garden and creates a blueprint shown below. He wants to place a corner-style bird bath where the X is located on the blueprint. The corner-style bird bath can only fit in a corner that is greater than 55 degrees. Determine if the bird bath can fit in the corner X by showing your work and solving for the measure of X. So this is one of those missing measurement problems where we have to kind of work our way back to this angle, okay? Because we don't have all the sides. This is not a right triangle. We can't assume that it is. I mean, we did show that this is a right triangle. Well, if that's a right triangle, we know that this is a straight line. This makes this a right triangle as well. So what we're going to have to do here is figure out the height of this thing. So we're going to have to figure out this intermediate height. Let's call this y. Because eventually, when we get to this angle over here, we can see that we're looking on this right angle here, or excuse me, from this angle x, it's going to be our opposite and hypotenuse. Okay, so we're eventually going to get to that point, but we got to figure out what y is first. Well, this is just a right triangle. Now, how do we figure out the missing side on a right triangle? Well, that's just a Pythagorean theorem problem. In which case, we've got a 15 squared plus a y squared is equal to the hypotenuse, is always across from the 90, of 45 squared. Okay, so we want to get this y height, so let's get that y by itself. Let's subtract the 15 squared from both sides. So our y squared is going to be equal to 45 squared minus 15 squared. But we're trying to get this y by itself, that individual height. We're not looking for y squared, we're looking for y. So we have to undo a square with a square root. So let's take the square root of both sides now. So our y is going to give us an approximation because we're going to be doing a square root. So let's go 3 decimal places. Let's go 3 decimal places because we were going to have that as an intermediate value here. Let me move that right there. So second x squared, so that opens up our square root function. Okay, 45 squared minus 15 squared. Okay. Then I hit our enter button, so we're going to see that that is approximately 42.426. So 42.426. Okay, we're going to need that. So that's an intermediate value. We're going to use that now. Okay, so this is 42.426 for this height. But now we can use our trig function. If I've got an opposite and hypotenuse, opposite hypotenuse once again is a sine function. So we're looking for this angle. Okay, so the sine of that x angle is the ratio opposite over hypotenuse, that 42.426 over the 54. Okay, now this is a missing angle problem. So if we're missing an angle, we have to use the converse, or excuse me, the inverse rather, the inverse functions here. So let's say that we've got the inverse sine of that ratio, 42.426 over 54, is going to be equal to our x degree angle. So let's put that in our calculator. So we've got the inverse sine, so second sine, okay, of that ratio, 42.426 divided by 54. So we're going to get approximately 51.7. Well, that's about a 52 degree angle. 52 degree angle. Well, does this answer the question? Well, if our angle is approximately 52 degrees, remember what they were looking for here. We need this bird bath can only fit in an angle that's greater than 55 degrees. Well, if it's not greater than 55, it's not going to fit. Well, 52, hopefully we can all agree, is definitely not greater than 55. All right? So our answer here is going to be no. Okay? No. The bird bath cannot fit in the corner because it is 52 degrees, okay, which is less than 55 degrees. Okay? So when you're explaining stuff, you want to show your work, use your formulas, have your conclusion, show what numbers you have to be able to reach that conclusion. 52 being less than 55, that's why our answer is no. Let's take a look at our next one here. All right. So we've got another missing angle problem here, or not missing angle, missing side, missing piece problem here. So it says we're going to solve for x. X is this distance from here to here. So we're going to work our way backwards to it again. So very often, if we're over here, we're going to work our way from outside in. So what do we know? Well, let's see. If this is a 20 degree angle, okay, we know that, well, this is 40. Well, if this is 40, this is a straight line. So we know that 180 minus that 40, okay, is 140 degrees. Okay, so that means that this is a 140 degree angle here. Now, what can we do with this information? Well, we know that the angles inside of a triangle have to add up to 180. So we got to figure out this angle right here. Okay, we're looking for this angle over here. So we know that it's going to be 180 minus the 140 minus that 20. So 180 minus the 140 minus the 20. in which case we get another 20. So this is a 20-degree angle as well. Now, this may not seem to help us very much, but actually it does, because you'll notice now that this triangle here, okay, this is a 20-degree angle, that's a 20-degree angle, two angles congruent, that makes this an isosceles triangle. So that means if this is 20 degrees and that's 20 degrees, that means that the sides opposite of those angles are also congruent. So that means that if this distance from here to here is 25, so is this. So this is also 25. So now we just have a basic trig function. Okay, we have this angle here. In relation to this angle, this is our adjacent and our hypotenuse. So we know it's a trig problem. So SOHCAHTOA, let's write it down. SOHCAHTOA. Okay, so in this particular case, we can see that with this adjacent and hypotenuse, we're going to be using our cosine function. So our cosine of that 40-degree angle is our adjacent, the x, over the hypotenuse, 25. Okay, so our unknown, once again, is in the numerator, so that means we're going to do some multiplication here. So our x is going to be at 25 times the cosine of the 40-degree angle. And let's figure out what that's going to be. 25 cosine of 40. So 25 cosine 40. So we're looking at about a 19.15. So in other words, a 19.2. So approximately 19.2. All right, number 25. So Steve is deriving the formula for the area of a circle. He cuts the sections and forms a parallelogram out of the sections as shown. Which two statements are true? Now, there was a video that we saw earlier in the year where imagine we were trying to figure out the area of a circle. So what they would do is they'd take an entire circle and they'd cut it in smaller pieces and smaller pieces and smaller pieces. Okay? Eventually smaller and smaller and smaller until eventually it became a parallelogram. Well, we can see here that this distance from the center to the edge, well, this is our radius, okay? Because that's just the definition of a radius, from the center to the edge. So that's this distance from here to here, okay? From the center to the edge of the circle, that's the radius, okay? We had also talked about how the base of this parallelogram, from left to right here, was half of the circumference, okay? And this is the height of this parallelogram. Once we got smaller and smaller pieces, we got this height of a parallelogram from here to here. So which ones are true? Now, they tell us that there are two statements that are going to be true here. So let's go line by line. The radius of the circle is half the height. Well, the radius is equal to the height. It's not half the height, it's equal to the height. Okay, equal to the height, that's why B is correct, A is not. The radius of the circle is equal to the base of the parallelogram. Well, this radius is definitely not equal to the base, so that's not true. Half the circumference of the circle is equal to the base. Well, yeah, this is our base of our parallelogram, and that's half of the circumference. So that's why it's going to be D. Well, they only told us to choose two, so E and F have to be wrong, but let's just double check. The circumference of the circle is equal to the base. Well, the base is half the circumference, not a full circumference. So that's why that one's false. And the circumference of the circle is equal to the height. Well, the circumference would be this and that. Well, there's no way these two added together can be equal to the height of the parallelogram. That wouldn't even make sense at all. So those are definitely incorrect. So that's why it's going to be B and D on those. All right. Let's keep moving forward here. So on numbers 26, 27, find the volumes of the given shapes. Now, the volume formulas are going to be given to you on your formula sheet here. So the formula sheet is going to be available on the test, so they'll have the formulas that we're going to need for those, because not all the formulas that we're going to need in the entire test are on there, but these are. So let's use this. So First thing, we have to figure out what kind of a shape this is. Well, this is going to be a prism. Specifically, it's a rectangular prism. Now, the volume formula for any general prism is BH, where B is the area of the base, the thing that this shape is sitting on, times its height. Okay, so our volume is equal to the base times its height. So we can see here that it's kind of sitting on this piece down here. It's sitting on this as the base, right? So it's 11 by 7 for the base. So it's 11 by 7 for the base, and we can see that it's 4 high. So let's multiply that through. 11 times 7 times 4. In which case we get 308. So our volume is going to be 308, and we're talking about feet, but a volume is cubic feet. Okay? 308 cubic feet. All right? Number 27 over here, we've got, this time we've got a pyramid. Now, pyramid, and we can see that it's the base of this, it's sitting on this shape down here, right? It's sitting on this shape. Okay. So it's actually a 12 by 12, so it's actually a square pyramid. Remember, they're categorized by their bases. So let's take a look at our formula for a pyramid. So a pyramid is 1/3 base times height, where our base is going to be the square. Okay? So our volume is equal to 1/3 big B base times our height. Let's plug our numbers in. So we have 1/3. Our base is a 12 by 12, right? So it's 12 by 12. That's our base. Times the height, and the height of the pyramid is a 10. Okay, so let's put that in our calculator. So we've got 1/3. So 1/3. All right, a 12 by 12. And then times the height. So we're going to have, 480. So our volume is going to be 480, and we're talking about centimeters. And since we're talking about volume, it's cubic centimeters. Okay? Let's go to the next page here. Oh, got another volume problem. So this time we have a prism again, but this is a triangular prism. Okay, triangular prism because the base that it's sitting on is this triangle down here. Okay, you can see that it's sitting on this triangle. So we knew that previously our volume for a prism was base times the height, where that big capital B, that's the area of the base. So in our formula sheet, okay, they actually have the area of a triangle is 1/2 small b h, okay? So our base is a triangle, so it's equals 1/2 of the base times the height. Now, which one's which, it really doesn't matter. We just know that a base and a height are 90 degrees from each other. So choose one, choose the other, it really doesn't matter. So our base is 1/2 of a 2 by 1. Okay, so that's what the B is. Let's put that here. So our volume is going to be 1/2 of the 2 by 1, 2 times 1. And the height of this is the 17 here. Okay, so let's do a little bit of mental math here. Well, 2 times 1 is 2. Half of 2 is 1. 1 times 17 is just 17. In this case, we're talking about cubic meters. All right. Let's take a look at our next one. So continuing on with three-dimensional shapes, says each of the two-dimensional figures shown will be rotated 360 degrees around a respective line, creating a three-dimensional figure. Choose the appropriate two-dimensional figure to identify the correct representation of the resulting three-dimensional figure. So we're imagining that we've got these lines here, right, that we're going to revolve these different shapes around to end up with these three-dimensional shapes to match them up. So let's just name these things. Let's call this one, I don't know, A, B, C, and D, okay? So if we took this circle and revolved it around that line, we can kind of imagine it would look like this donut. If you looked at this donut from the side, right, you'd have this line that would end up going through here and just kind of revolving around it. Okay, so let's call that A. B, if we took this semicircle and revolved it around that line, we're going to end up with a sphere, just like over here. Now this one's a rectangle. If we revolve that rectangle around that line, you end up with a cylinder. And our last one is a triangle that if we revolve around that line, we end up with a cone. Okay? So you got to kind of imagine what these different shapes look like when we revolve them around some kind of an axle or a respective line there. All right, let's talk about our cross sections. What two-dimensional cross sections could be obtained from a rectangular prism? Well, rectangular prisms, once again, we're talking about cross sections. Imagining our three-dimensional shape where if we would section it horizontally or vertically, cutting it straight up and down, what would it look like? Or even at an angle, if we cut it at an angle. So for a rectangular prism, there's really only two options. It's either going to be a rectangle or square. Okay? One of those. Okay? Now, for a two-dimensional cross-section obtained from a cone, so we've got a picture of a cone up here. So if you can kind of imagine it, if you took a horizontal cross-section, basically you're looking at it from the top down. Well, from the top down, it would look like a circle. From the side, if you're looking at this cone directly from the side, it looks like a triangle. Okay? Now, if we took a diagonal slice, a section that went diagonally through the sides here, you end up with an ellipse. But if you took a section that went through the side and through the base, you end up with a parabola. Okay? So there was a whole section on those. We even had links that allowed you to kind of play around with those different kinds of shapes and manipulate them and kind of see what they look like from the different sections. All right, let's take a look at number 32. A wood log is approximately cylindrical, okay, with the dimensions of the diameter of 1.5 feet and a height of 4.5 feet. The log weighs 206.8 pounds. What is the density of the wood to the nearest whole number? All right, now previously we had talked about density, but with populations. Now density in more of a scientific kind of a thought is, you know, how dense something is, whether it could float or whether it would sink or whatnot. So the way that we would think about this, well, first, let's figure out this cylinder. Now from our formula sheet, we've talked about cylinders before. Our volume is going to be pi r squared h. Okay, so we got to figure that out first. Okay, so our volume is pi r squared h. So let's plug in what we know. Well, pi is just pi. Now radius. Well, they didn't give us a radius, they gave us a diameter. Well, if the diameter is 1.5, the radius is going to be half of that. Okay? The radius is going to be half of that 1.5. So let's divide that by 2. So we're going to have a radius of 0.75. Okay? So our radius is going to be a 0.75 that we're going to have to square. Okay? So pi 0.75 squared, and then we're going to multiply that by the height. In this case, they told us that it was 4.5. Okay, so let's figure out our volume. So pi, so second, the caret, pi, our radius was a 7.5, so times a 0.75, we have to square that, and our height was a 4.5, okay, times a 4.5. So our volume here is approximately 7.952. So it's 7.952, and this is in cubic feet. Now, this is an intermediate value because we're not done yet. Because the question is, what's the density? We haven't even talked about density yet. We're just talking about the shape so far. So we've got this cylinder here. But how do we figure out the density? Well, in the strictest sense, a density is equal to a weight or a mass divided by area or volume. Okay, so if we're looking for density, what do we have? So our density, we do have a weight. They told us that the log weighed 206.8 pounds. And we calculated the volume at 7.952 cubic feet. All right, so our density, we're just going to divide. So 206.8, and we're going to divide it by that 7.952. In which case we get a 26.0, because they told us to round to the nearest whole number, so we're looking at 26 pounds per cubic foot. Okay? Let's go on to the next page. All right, so we got some more volume stuff here. So an ice cream shop serves small and large scoops of ice cream. Each scoop is sphere-shaped. Well, that's important. Each scoop is sphere-shaped. Each small scoop has a diameter of approximately 6 centimeters. Each large scoop, okay, has a diameter of approximately 10 centimeters. What is the difference? So what is the difference in cubic centimeters between a large scoop of ice cream and a small scoop of ice cream? Round your answer to the nearest tenth. So we're going to have to think about what this means. Now, a sphere, so if each one is a sphere, let's just imagine what this looks like. So we've got small scoops, and we've got large scoops, okay? And they tell us a diameter, okay, for the small and the large. So the diameter for the small one was 6 centimeters. The diameter for the large one was 10, okay? Now, let's think about this. For a sphere in our formula sheet, a sphere is 4/3 pi r cubed. So we're going to have to figure out the difference. Now, difference means that we're subtracting the big one minus the small one, all right? So we need the large minus the small. Okay, that's going to be our volume difference. Okay, so we need each volume in here. So for the volume of any sphere, it's 4/3 pi r cubed. Okay, but they didn't give us the radius, but we can figure out the radius. If the diameter was 6, our radius is 3, half of that. If our diameter is 10, our radius for the large one is 5, half of that 10, okay? So we're going to do that twice. So we've got our volume. It's going to be our large scoop, which is 4/3 pi. Our radius is a 5 cubed. From that, we're going to subtract the small one, 4/3 pi. Our radius was a 3, and we're going to cube that. Okay? So let's put that in our calculator. Let's clear that out. So I've got a 4/3, so 4 divided by 3 pi, okay, second caret, so there's our pi. Our radius was 5, and caret to the third. So now that's the 4/3 pi 5 to the third. Now I'm going to use this little right arrow here. It's going to move the cursor down to where I can actually put the minus here. Because if I don't, it'll accidentally put the minus up here as the rest of the exponent. We don't want to do that. So 4/3 once again. So 4/3 pi. And our radius this time was a 3 cubed. Okay, hit that enter button. And our difference is going to be 410.50. So 410.5. So 410.5, and that's cubic centimeters. Cubic centimeters. So that's the difference between the two. Now, you didn't necessarily have to do this all in one shot. You could have figured out this one and then subtracted the small one individually. You should still have gotten 410.5. Either way you get it, okay? All right, number 34. Solve for the volume of a cube that is not taken up by the sphere. Use pi. So this is one of those kinds of problems where we're imagining we've got this sphere inside of this box, right? This cube. They even tell us it's a cube, all right? So they only give us one measurement, so we have to make an assumption. Well, if it's a cube, we know that all the sides are going to be the same, okay, length, width, and height. And we're going to assume that the sphere fits exactly inside the cube, left to right, up and down, back to front. So that means that the diameter is also 8 meters. Well, if the diameter is 8 meters, then our radius is 4 meters. We're going to use that once again when we are going to calculate our sphere, just like we did in that problem above. So the volume not taken up by the sphere. So our total volume is the volume of the cube minus the volume of the sphere. So a cube is just a square prism. So our volume is going to be base times height. Our sphere, once again, is 4/3 pi r cubed. So let's plug those in. So our base is an 8 by 8. 8 times our height of 8 minus 4/3 pi, and our radius is the 4. We got to cube that. So let's put that in our calculator. So we've got an 8 times 8 times 8, okay? And from that we're going to subtract 4/3, 4 divided by 3, pi, second caret, and then 4 to the third power. So 4 caret 3. That raises it all to the third power there. Hit that enter button, and we get 243.917. So we're going one decimal place, so 243.9. So 243.9, and we're talking about meters cubed. All right. All right, let's take a look at the next page. All right, so a smaller model is going to be made of the shape shown. If the new radius is 5 feet, what is the volume of the smaller model? So this is a volume problem, but it's also a dilation problem because we're going to make a smaller model from the shape shown, right? So if we're going to have a dilation, we're going to make it smaller. So we have to figure out a scale factor, and we got to figure out how much smaller it's going to get. So once again, our scale factor, okay, is our new divided by our old, our prime divided by our non-prime. So our new divided by our old, or the finish divided by the start, or however you want to think about it. So in this particular case, our scale factor, our new radius is 5 feet. Okay. Our current radius, the old radius, is the 40. So we want each one of these to be 5. Okay. divide that by 40. So 5 divided by 40 is 0.125. So 0.125. This is our scale factor. We're going to have to use that. So we're going to apply this scale factor. We're going to multiply this scale factor by every measurement over here, right? So let's multiply it by our 75. So 75 times that 0.125 is a 9.375. Okay, 200 times that 0.125 is a 25. Okay, now we know that the radius here is going to be the same thing as this radius over here. So this is also 5 feet. We're going to use that. So we're looking for the volume of the smaller model. Now that we've got all the smaller measurements, let's figure out the volume here. So the total volume, we've got a composite shape here. We've got a cone up top, cylinder down the bottom. So our volume altogether is the cone volume plus the cylinder volume. Okay? Now for a cone, it's 1/3 pi r squared h. So 1/3 pi r squared h. Always like to write my formulas down so I know what to plug in. And a cylinder is pi r squared h plus pi r squared h. So let's plug in what we know. Let's substitute our values in. So we got a 1/3 pi. Our radius is 5 for the cone. So it's a radius for the other one as well. Our height of the cone is 9.375. So times 9.375. Okay. And we're going to add to that pi, the radius once again, 5 squared, and the height of just the cylinder is 25. So let's put all this business into our calculator here. So let's move it here. So we've got 1/3, so 1 divided by 3, pi. Our radius was 5, we have to square it, and then multiply it by 9.375, okay? And from that, or excuse me, to that, we're going to add that pi, 5 squared, 25. So pi, 5 squared times 25. So altogether, we should end up with 2208.93 or 2208.9. So 2208.9, and we're talking about feet. So cubic feet is the volume of the new shape. All right, last little bit here. All right, so this is going to be helpful to do a little bit of drawing here as well. So it says, put a check mark for yes in the table if the quadrilateral has a certain number of pairs of angles, pairs of sides, or diagonals. Write the number in the table instead. Okay, so this is basically a lot of vocabulary here. So we're going to do a little bit of drawing, and this will help us kind of think about what's happening with our different shapes here. And then we'll just go down the line. So our first one is a parallelogram. Now, a parallelogram, if we were to draw this thing, okay, let's say it looks like, oh, I don't know, something looks like this. Okay, so a parallelogram. So parallelogram, by definition, opposite sides are parallel. Okay, so are opposite sides parallel? Yes. Okay, definitely. Are opposite sides congruent? Now, previously we saw that a parallelogram is kind of like, imagine a rectangle. A rectangle got kind of leaned over, right? So we know that the opposite sides are going to be congruent to each other, okay? Are all the sides congruent? No, definitely not. Are consecutive sides congruent? Now, consecutive just means one after the other. So that would say that this was congruent to that. Well, we can see that one is longer than the other, so that's not going to work either, okay? Let's see. Are opposite angles congruent? So we're talking about this angle over here being congruent to this angle over here, okay? Those are definitely going to be congruent to each other. Same thing over here. This angle here and this angle here are going to be congruent to each other. So that works out. Are opposite angles supplementary? Now, remembering our definition of supplementary. Supplementary means adding up to 180. Well, these two angles are less than 90 degrees. Well, two things less than 90 cannot possibly add up to 180. Okay, so that's not going to be true. Are consecutive angles supplementary? Well, yeah, if you think about it, we have two parallels here and a transversal. This is same side, interior. Those are definitely supplementary. They add up to 180. Okay. Are consecutive angles congruent? Well, this angle is not equal to that angle, so no. Are all the angles right? Not at all. Not right angles. Are the diagonals congruent? So we're talking about the diagonals. So the diagonal would be talking about from here and here. Well, this one's longer than that one, so definitely not. Okay. Are the angles perpendicular? Are the diagonals perpendicular? Well, these do not necessarily cross at 90-degree angles, so we can't say that that's true either. Do the diagonals bisect each other? Actually, they do. Okay, when these cross, it gets cut in half. So this is congruent to that. This is congruent to that. Okay, so that is definitely true. Okay. Do the diagonals bisect the opposite angles? So it's asking, are these angles being bisected by the diagonals? Answer there is no. All right, let's take a look at a rectangle. Well, rectangles are rectangles. So let's draw ourselves a little rectangle here. Okay, so rectangles. Well, what do we know about rectangles? Are opposite sides parallel? Yeah, opposite sides are parallel on a rectangle. Are opposite sides congruent? Yes. So the top and the bottom are congruent to each other. The left side and the right side are congruent to each other, so that's true. Are all the sides congruent? Well, not all the sides. All the sides are definitely not congruent. Are consecutive sides congruent? So that means that this, then that, are those the same length? Absolutely not. Okay. Are opposite angles congruent? Well, what do we know about the angles on a rectangle? Well, they're all 90-degree angles. So are the opposite angles congruent? Well, a 90 is congruent to 90, so absolutely. Are opposite angles supplementary? Well, that angle and that angle, 90 and 90, that's 180. 90 and 90, that's 180. So that works as well. Are consecutive angles supplementary? So that would mean this and this, 90 and 90 is 180, or 90 and 90, that's 180. 90 and 90, that's also 180. So yeah, absolutely, that works. Are consecutive angles congruent? Consecutive angles congruent? Well, yeah, consecutive angles are congruent. Okay, because 90 is congruent to 90, 90 is congruent to 90. Are all the angles right? Yes, they are. Are the diagonals congruent? So the diagonals, okay, when you take a rectangle, those are also congruent. Are the diagonals perpendicular? Do these cross at 90 degrees? Not necessarily. Do the diagonals bisect each other? Matter of fact, they do. Okay? They cut each other in half. Same thing here. Okay? And do the diagonals bisect each other? No, they don't. Okay? A rhombus. Now, a rhombus we've seen is kind of like a diamond or a leaned over square. So we would see that the diagonals, or all four sides, are going to be the same length. Okay, I'm going to do my best to kind of sketch this out here. Okay, so imagine a square that's kind of leaned over. Okay, so we know that all four sides are going to be congruent. Okay, so are opposite sides parallel? Yes. This side parallel to that side, this side parallel to that side. Absolutely. Okay. Opposite sides congruent. Well, they're all the same length, as a matter of fact. So they're all congruent. Are consecutive sides congruent? Well, if they're all congruent, then that one's congruent to that one's congruent to that one, and consecutively around the rhombus. Are opposite angles congruent? Yeah. This angle, opposite of this angle, same angle. This angle, opposite this angle, same angle. Are opposite angles supplementary? Well, that would mean these two angles add up to 90. Well, something less than 90 and something less than 90 are not going to add up to 180. So that doesn't make sense. Okay. Are consecutive angles supplementary? Yeah, because once again, these are parallel to each other. This is a transversal. These are same side interior angles. So those are supplementary. Absolutely. Are consecutive angles congruent? Well, this is not congruent to that. Are all the angles right? Absolutely not. Are the diagonals congruent? So the diagonals, well, this one is longer than this one. Okay, so that doesn't work. Are the diagonals perpendicular? Matter of fact, they are. When they cross at 90-degree angles. Do the diagonals bisect each other? They do indeed bisect each other. Okay? And do the diagonals bisect the opposite angles? Yes. These end up bisecting these angles in the corners as well. All right? So let's talk about a square. Well, squares are pretty easy to deal with. Draw myself a little square here. Okay. What do we know about squares? All four sides are the same. All angles are 90-degree angles. Okay. Are the opposite sides parallel? Yes, they are. Are opposite sides congruent? Yes, they are. Are all sides congruent? Well, it's a square. Sure. Are consecutive sides congruent? Absolutely. All four sides are congruent, so the consecutive sides are congruent as well. Are the opposite angles congruent? Well, 90 and 90, 90 and 90, those are definitely congruent to each other. All 90s are congruent. Are the opposite angles supplementary? Well, 90 plus 90, or 90 plus 90, adds up to 180, so yes. Are consecutive angles supplementary? So 90 plus 90, that's 180. 90 and 90, that's 180. Same thing here, same thing there. Okay? Are consecutive angles congruent? Well, all the 90s are congruent, so absolutely. Are all the angles right? Yes, they are. Are all the diagonals congruent? Are the diagonals congruent? So you've got this diagonal here congruent to that diagonal there. Absolutely, those are congruent. Are the diagonals perpendicular? Matter of fact, they are. Okay. Do the diagonals bisect each other? They do. Matter of fact, all of these diagonals will be the same length as each other. And the angles get bisected too, because these end up being 45, 45, 90s. So 45 and 45 add up to 90, so it cuts it in half. Okay, so that's a nice thing about a square. It kind of, well, checks all the boxes, so to speak. Well, let's talk about a trapezoid. Now, a trapezoid is a four-sided shape. Let's draw this thing. A four-sided shape, let's say, looks like, oh, I don't know, something more or less like this, where two sides are definitely parallel to each other, okay, and two sides aren't. Okay, so these two sides are parallel to each other. These other two sides are not. Okay, so are opposite sides parallel? Well, one pair is. This side and that side, those are parallel, so one pair. Okay, are opposite sides congruent? Well, not necessarily. Okay. Because, I mean, as far as trapezoid, one is definitely going to be longer than the other, so all sides are not congruent. Okay. Are all sides congruent? Not necessarily. Well, as a matter of fact, not at all. Because, once again, one has to be longer than the other. Are consecutive sides congruent? Nope. Are opposite angles congruent? Well, that would say that this angle and this angle was the same because they're opposite of each other. Well, that makes no sense. Are opposite angles supplementary? So that would assume that these two add up to 180, those two add up to 180. Can't make that assumption. Are consecutive angles supplementary? Okay? Well, two of them are. Because once again, if you think about it, we've got two parallel lines, right? That means you've got two transversals. So you've got same side interior angles are automatically supplementary. Okay? This angle and this angle, if you add those two together, they're going to add up to 180. Okay? Okay, so consecutive angles supplementary, two pair of them are. Okay? These two add up to 180, those two add up to 180. Are consecutive angles congruent? Absolutely not. Are all the angles right? Nope. Are all the diagonals congruent? Well, that would assume that this is the same length as that. And hopefully you can see that that doesn't make sense. Are the diagonals perpendicular? Not necessarily. Do the diagonals bisect each other? No, they do not. Do the diagonals bisect the opposite angles? No, they do not. All right, so trapezoids are kind of special in the other way around. They don't check all the boxes. They're kind of special in a different kind of a way. An isosceles trapezoid. Now, if this is a trapezoid, what's an isosceles trapezoid? Well, previously in life, we saw an isosceles triangle. An isosceles triangle had two sides that were congruent. So let's make two of the sides congruent. Okay, this side's congruent to that side. This side is parallel to that side. And these sides are obviously not congruent to each other. So, are opposite sides parallel? Well, one pair are. This and this, those are parallel, but the other two are not. Are opposite sides congruent? Well, one pair is. Okay, the other pair isn't. Are all the sides congruent? No. Are consecutive sides congruent? No. Are opposite angles congruent? Well, opposite angles would say that this angle and this angle were congruent. Well, you can see this is greater than 90, that's less than 90. Those are two different angles, so opposite angles are not congruent. Are opposite angles supplementary? Well, we can't make that assumption either. Well, let's see. Supplementary. Well, we know that same side, because this is our parallel here. So we know that this and this are supplementary. This and this are supplementary. But are the opposite angles supplementary? Well, let's see. The consecutive angles, two pair are. Sorry, I skipped one. Are the opposite angles supplementary? Well, we can't assume that those two are. Okay. Are consecutive angles congruent? Well, consecutive angles are going to be congruent. If you look at these two at the top, they're going to be the same angle. These two at the bottom, they're going to be the same angle, even though I have different lines here. I was just kind of trying to illustrate a point. But yeah. Okay, so the tops and the bottoms are congruent angles. Let's see, are all the angles right? Absolutely not. Are the diagonals congruent? Well, if we look at this diagonal and that diagonal, yeah, they're going to be congruent with each other. Okay? Are the diagonals perpendicular? Can't prove that. Do the diagonals bisect each other? Definitely not, because this one's shorter than that. Do the diagonals bisect the opposite angles? No, they do not. Okay? And our last one is a kite. Now, a kite, kind of like one of those little Charlie Brown kites, right? Where you'll have two sides congruent to each other. Let me bring that out. These two sides are congruent to each other. Okay? And you can see it kind of splits it down the middle here as far as the diagonal. Diagonal runs that way too. Okay? So what do we see? Are opposite sides parallel? Well, this side and that side, they're not the same slope. They're not parallel. Okay? Are opposite sides congruent? Well, this side shorter than that side. Definitely not. Okay? Are all sides congruent? Nope. If two opposite sides aren't, all sides aren't. Are consecutive sides congruent? Well, you'll see that the top here, these two are congruent to each other. These two are congruent to each other. So we'll have two pair. Are opposite angles congruent? Now, these angles here and here are congruent to each other. These two are not. So one pair. Okay? So these two, that one pair of angles are congruent. Are opposite angles supplementary? Nope. Are consecutive angles supplementary? Not at all. Are consecutive angles congruent? No, these are different angles. Are all the angles right? Absolutely not. Are the diagonals congruent? Well, this is longer, this one is longer than that one, so definitely not. Are the diagonals perpendicular? Actually, they cross each other at 90-degree angles. Okay? Once again, imagining the kites that we used to build when we were little kids. Put two sticks at 90-degree angles. Works just like that. Okay? Do the diagonals bisect each other? No. Okay, this, however, bisects this. So we can see that this length from here is the same length from here to here. Okay? So one pair is. This one is definitely shorter than this one. So those are not. And do the diagonals bisect opposite angles? Well, this diagonal doesn't bisect these angles, but this diagonal bisects these angles over here. Okay, so in this case, one pair. All right, so lots of vocabulary as we're getting ready for the LEAP test. Check out the videos, all the videos from all the previous lessons that we saw. Be ready for the test tomorrow, and good luck.